more than 90% of all installed wastewater treatment plants around the world is using a technology that was invented 100 years ago. We typically build these treatment plants outside the cities. We collect the waste, build pipes, take the water outside the cities, treat the water there, and the further, the better. And the reason for this is that these treatment plants are usually very ugly, and they typically also smell. The problem is that these days, there's less and less water around the world, and there are very seriously water scarce areas. And as officials are looking high and low for more water so they can provide the ever-increasing urban population, they realize that the richest source of water is actually in the wastewater treatment plants. And what follows is that around the world, increasingly recognized that the urban water scarcity can be only addressed if we recycle the water. But we just established that all these wastewater treatment plants are outside the cities. It doesn't really make sense to take all the water, treat it outside the cities, so that then we build new piping and maintain all that piping so that we can pump back the treated water into the cities. But who would want to live next to these treatment plants? So here lies the challenge. We need a new solution, a solution that addresses the order problem, addresses the space problem, so it's much smaller in space. It's also something that you wouldn't mind either live or work next door to. And here comes the Organica solution. What you see here is a wastewater treatment plant of a community outside Budapest. This is, in fact, a botanical garden. Once you have this solution, you can build these inside the cities, close to where we live, close to where we work. Because these treatment plants are much smaller in footprint, use considerably less energy, produce less sludge, which is an important element in operations, and as you can see, they are aesthetic. In the following chapters, we will examine why is it possible that these treatment plants are smaller, use less energy, and produce less sludge. Let's take a look at the smaller footprint aspect. In order to understand how these treatment plants work, we need to go back and establish the base and comparison. So we will take a look how a traditional treatment plant works, just for a few minutes. So in a traditional treatment plant, we have these huge concrete reactors with fine bubble aeration at the bottom, and we have 3 to 5 kilograms of biomass swimming in the water. That translates to, for those of you from the industry, 3,000 to 5,000 MLSS. But basically what we have is tiny organisms swimming in the water, consuming the dissolved organic matter, building it into their bodies. Now, for comparison reasons, keep in mind that we have established that we have 3 to 5 kilograms of these hungry mouths swimming around doing the work for us, and there are about 600 to 800 kinds of those organisms, which we call 600 to 800 species. And of course, we have fine bubble aeration because all of these organisms need to breathe while they eat. Okay? So now let's take a look at it. How is an Organica plant different? In an Organica plant, we take the same reactors. We put plant tracks on top. And on the plant tracks, we have the plants and the roots of the plants dangle into the water about 1.5 meters. It's important to remember that the plants don't treat the water. People usually think, just looking at these treatment plants, these beautiful botanical gardens, that, oh, how beautiful it is, the plants are treating the water. The role of the plants, in fact, is to provide habitat in their root zone for a whole number of additional organisms. So now you can have not only the ones who are swimming in the water, which are the species who are adapted to swimming all the time, But now that you have the root zone in the water, now you are inviting those species that are adapted to different conditions. So now they attach themselves to the root. And as we will see in the next few minutes, there are tremendous advantages of this feature. One of the reasons is because the plant roots, as a natural substrate, invite a very large variety of organisms. The other aspect is that plant roots are enormous in surface area. We'll see videos showing that feature. So there's a lot of surface, which means there's a lot of place for organisms to attach to. That means we can keep a lot of organisms in a small space. We are increasing density, if you want population density. The specific or interesting feature of the roots is that they don't really grow much deeper than a meter and a half, 2 meters. But we would like to fill the entire reactor, and remember, these are 5, 6 meters deep. We'd like to fill the entire reactor with this habitat, because that means that we can fill the entire reactors with more population, so we can make the whole system more efficient. So we developed this artificial root system, if you want. We call it a biomodule, that mimics the characteristics of the roots. Again, for the purpose so we can provide additional habitat in the reactors. The result is that we can keep 4 times as much biomass in a cubic meter of reactor space and 4 times as many species. So we have a much larger biodiversity and many more creatures doing the work for us. Let's take a quick look at the roots. As I mentioned, you see a close-up of the roots here. And on this CT, computer tomography picture here, or video, you can see the spatial matrix of the roots. And you can see that under the microscope, it really provides a tremendous surface area. That's the explanation why we can keep that much more biomass in the reactors. Another interesting element of the roots is that the roots are alive, naturally. And the organisms that attach themselves to the roots live in a symbiosis with the roots. For example, plants pump oxygen into their roots. And some of the inner layers of the organism, which is called, by the way, biofilm, the biofilm that develops on the roots, are receiving some of their oxygen supply through the plants. Also, there is a material exchange. Enzymes come and go between the root surface and the biofilm. And what is the result is a very healthy biofilm, a very healthy community. And we really care about the health of that community because that community does the work for us. So in summary, let's keep in mind that we have increased the biodiversity by 4-fold. And we have increased the number of organisms that we can keep there, the volume, also 4-fold. We can have more than 12 kilograms of biomass in each cubic meter of reactor space occupied by either the roots and the biomodules. And it also comes to reason that if you can increase the density that much more, that means that you can make the treatment plants that much smaller for the same capacity. So in comparison to traditional activated sludge plant, Organica plants tend to be as much as 50 to 60% smaller. In the next few minutes, let's take a look at it. How is it possible that the footprint is that smaller? The plants are selected for their root structure, or based on the root structure, and on the root mass, because we are interested in the habitat that they can provide. But it's very important to note that we always use locally available plants. It's never necessary to ship plants across borders. You will also see on this slide that there is a greenhouse around the plants because it is important to maintain 6 to 8 degrees centigrade as ambient temperature for the plants and for the whole ecology to work properly. Greenhouses are industrial buildings that are manufactured in large quantities, actually usually in hectares. So as such, it's a very inexpensive type of building, and they come with various features all pre-installed temperature control and shading and misting equipment, and even wind speedometers that automatically close the windows of the greenhouses. Again, the role of the greenhouse is to provide a minimum 6 to 8 degrees ambient temperature. The treatment plants, the Organica plants, are designed as a very compact structure. As you can see on the right-hand side of the slide, this is where we have the reactors, the fine bubble aeration panels at the bottom of the reactors. You can see the biomodules, the plant roots in between, the plant tracks, the plants above that, and the enclosing greenhouse. On the left-hand side, you can see the mechanical equipment, typically in multi-story arrangement to provide a spatially very efficient solution. That means that it is in these sections where you will find the headworks, sludge treatment, blowers, control room, and even phase separation. In the Organica plants, as you will see later, it is possible to forego the clarifier, the traditional large clarifiers, and directly go from the biological reactors to a microfiltration unit. This way, it is possible to save all that space and really create a very compact structure. Now let's take a look at it. How is it possible that the Organica plants are using much less energy? In order to understand that, we have to go deep into the reactor, and we have to take a look at the biomass that develops on the root and on the biofilm. Remember, we have established that there are 4 times as many species and also 4 times the volume of the biomass. But how is that possible, and what does it look like? Let's take a look at these pictures. What you see on the left-hand side is a typical biofilm that grows on the plant root. And for comparison reasons, you see a typical MBBR carrier with the corresponding biofilm that grows on that. What you see on the right-hand side, MBBR, stands for moving bed bioreactor. And in those technologies, what you have is these little tiny, about 1 centimeter diameter little plastic carriers that are put into the water to allow organisms to grow on that. The reason I'm showing these 2 slides, and what you see is on the top, is the right scale comparison. To see the comparison of the biofilm that grows on the plant root or the biomodule compared to the plastic carrier that you would find in a traditional MBBR plant. And in order to compare, let's take a look at the next picture, where on the left-hand side, you see the structure in a graphical representation of the biofilm that grows in an Organica system. And on the right-hand side, you see the biofilm that would grow on an MBBR carrier. There are very important differences. For one, as you can see, the one on the left-hand side is considerably more thicker. It's like 2 orders of magnitude deeper. But it's also, what you can see is that the structure is very loose. It's like seaweed. It's very fluffy. And that, on the left-hand side, in an Organica plant, that fluffy structure allows for a much better mass transfer characteristics. So both for the food can be much better absorbed in a much more efficient way, as well as the necessary oxygen for all these organisms that form or compose this biofilm. On the next slide, on the left-hand side, you can see a typical biomodule. Maybe you can make out the construction worker on the lower left-hand corner. And then on the right-hand side, you see the biofilm that grows on this media. And again, it's important to note that you have a lot of this biomass. Remember, it's more than 12 kilos per cubic meter. But also you can see it's very fluffy. And there's a third element that is important to notice here, that as we look at this picture, we can see that the water is relatively clear. So keep in mind that we're keeping all this biomass in the reactor, but all of the biomass is attached. very little of the creatures, very few of them, are swimming. That means that the suspended matter in the water is very low. This is why it's relatively clear. Now, why is this important? It's very important because it directly impacts how efficiently you can run a treatment plant. What you see on the next slide is a schematic. What happens? How does the oxygen get actually into the water? The organisms that use the oxygen need it in a dissolved matter. So we have the fine bubble aeration in every traditional treatment plant as well as in an Organica plant. And these tiny little bubbles are traveling from the bottom of the reactor all the way up to the top, 5-6 meters. And during this travel, these are really, really tiny bubbles. And during this travel is that the air from the bubble and the oxygen that's inside the bubble dissolves, makes its way, diffuses into the water around it. Now, in clean water, this diffusion, this transfer of oxygen between the bubble and the water is uninhibited. And actually, by definition, the efficiency of the transfer is considered 1 for clean water. Now, the moment you start to have particles in the water, those particles interfere on the surface of these little bubbles with the transfer. So the more little particle attaches to the bubble, the less ability for the oxygen to transfer into the water. So that means the oxygen transfer efficiency, actually that coefficient, which is called the oxygen transfer coefficient, is less and less the more and more particles you have in the water. So in the next slide, what you see is a graph. On the vertical axis, you see what is called the oxygen, the alpha, which is the oxygen transfer efficiency. And on the horizontal axis, you see how much particles are in the water, which is TSS really, which is for total suspended solids. Now, in a traditional, let's say an MBR, which stands for membrane bioreactor, which is run by, let's say, 12 kilograms of biomass in the water, that oxygen transfer efficiency may be as low as 0.5 or even lower because you have that many particles in the water in suspension. In a traditional activity sludge plant, which is, let's say, is being run at 4,000 mLSS, that alpha, the oxygen transfer efficiency, will be around 0.55. Because that's if you have like 4,000 milligrams of material in suspension. Now, in an Organica plant, because all the biomass, you have a lot of biomass, but all of it is attached, very little is swimming in the water. That means that you can keep the oxygen transfer efficiency above 0.9. And the difference between the two, in other words, between the 0.9 and 0.55 or 0.5 or even lower numbers, is clear energy savings. So the lower energy use has a very simple physical explanation. It can be traced back to the higher oxygen transfer efficiency. The largest cost component in running a wastewater treatment plant is actually energy use. So that's why the lower energy, 30, 40, sometimes 50% lower energy use actually translates to that much lower operational expenses. So we can establish that Organica treatment plants cost less to operate. In addition to the cost of energy, the next most important cost component in running a wastewater treatment plant is sludge handling. So it is very important how much sludge is being produced because it directly influences the operational cost. In Organica plants, there is lower sludge production. And in the next few minutes, we take a look at it. How is it possible? Why is it that less sludge is produced in these treatment plants? We have established a few minutes ago that in an Organica plant, you have a larger biodiversity and you have larger biomass. It is really the larger biodiversity that becomes very important from the sludge production point of view. We take the reactors that we looked at and we arrange them in a series, as you can see it on this slide. As the water goes from the left to the right, the composition of the waters changes. In the beginning, there's a lot of ammonia in the water and a lot of food. So you will see organisms in the first reactor that are adapted to those kind of conditions. But as the water goes from one reactor to the other, and different organisms will adapt to the various conditions, as the water makes its way from left to the right in these reactors, and notice that there are at least 6 reactors in a series here. Different ecologies, different communities will develop in each tank. So let's take the example. In the beginning, there's a lot of ammonia from urine, and then there's a lot of food from the other stuff. Okay? That means you will find organisms that are adapted to those conditions. And as the water goes from one tank to the other, and then it reaches to the end, on the other end of the train, there is very little food left. And of course, there's no ammonia left if you do a good job. But when you have very little food left, you need organisms that are adapted to those conditions, so they can screen out the tiny little percentages that are left in the last reactor. What we find, once you have a larger number of organisms, and we do, what is called the food chain effect will come to life. Because we have not only bacteria, but higher level of organisms, such as worms and mussels and fish even at the end, the higher level of organisms will always feed on the lower one. You can look at it as a system where the food source, which is the wastewater, and the contaminants in the water are actually fueling a larger ecosystem. And of course, for a larger ecosystem, a more complex ecosystem, you need more food. At the end of the day, as these creatures are feeding on each other, you will have less material left, which translates to lower sludge production. So let's take a look at some of the characters that are playing in this game. These organisms that you see on the screen now are tiny little organisms that are swimming around. They're in suspension in the water. They take the dissolved organic matter and they'll build into their bodies. These are the little guys. What you see on the next one is the big guy who is attached to the root on the left-hand side. And is waiting until the little guy shows up. And the little guy makes its way into its mouth. And then, with a big gulp, the little guy becomes dissolved organic matter in the belly of the big guy. This is predation. And then another one will come, which is called a grazer, and will eat this big guy, but this is an even bigger guy. And so the food chain builds up, and the organisms feed on each other. The next one is an amoeba. It's a one-cell organism, and you can see how on the top of the screen it will gobble up the dirt there. We call it the vacuum cleaner. Or the next one is an aquatic worm, and you can see how it's looking for food and how the food makes its way down its digestive tract. You see, this is really like National Geographic under the microscope. But these guys are doing vital work for us. They clean the wastewater for us. The next one is these organisms, again, are attached to the root. And these can be found towards the end of the treatment train. These have large mouths and cilia around the edge, and they filter a lot of water through their bodies. So the last little bits of colloids and components can be taken out of the water. Very efficient filtering mechanism here. All in all, in addition to the energy savings, it is the lower sludge production that is an important component that contributes to the fact these treatment plants are run by significantly lower operating costs. And remember, underneath this beautiful botanical garden, there is a reactor teeming with life, with thousands of species doing the job for us. So we have established that we have a treatment solution that is small in footprint, uses much less energy, produces less sludge, and it's actually beautiful. It's appealing. Where can we use it? Which are the applications? I'm going to show you a few of the many possibilities, but it's very important to start with the understanding that there is no limit in terms of capacity. You can use the Organica treatment solution from a treatment plant that serves a few thousand people all the way to large-scale plants which serve 1 million people. And you will see in the examples for all of these. An interesting aspect of the Organica solution is that because of the aesthetic appeal, it has a positive effect on the environment. This treatment plant that you see on the screen now, when we built this, it actually replaced an old treatment plant. And once we were finished, the builders, the developers in the community approached the city council, and they asked the city council to change the zoning rules. So what used to be the buffer zone, it should be eliminated. And so it was indeed reduced from 350 meters to 20 meters. And within a year after we built the treatment plant, developers started to build housing around the treatment plant. And actually those houses today sell for €500,000 each. We believe it's because of the presence of the beautiful treatment plant. The next example is in an industrial office park, where it was very important for the developer, not so much whether the treatment plant is 20 or 30% smaller, which it is, but just as important was the effect on the rent that he can collect next door. To the left of the treatment plant, there are offices. There's a huge difference in economic value, whether he has to give a discount because the office is next to a wastewater treatment plant, or maybe he can charge a little bit extra because it's next to the botanical garden. So we can establish that in addition to treatment plants having physical footprints, they also have psychological footprint. What do we mean by psychological footprint? If I ask you the question that how close would you buy a house, or how close would you live in an apartment to a treatment plant? The answer is usually not even a number. It's usually as far as possible. When in fact, what it means is that there is a detrimental effect of the treatment plant on the value of the real estate around it. So it's not only where it ends, not only the fence around it, but in the neighborhood, in this immediately surrounding area. What we see in the Organica plants, that effect is actually a positive effect. This treatment plant is in France. And you can see from the inside, it has a beautiful color scheme. Or the next one, where actually the plants add additional dimensions to the color. Or the next one is in a historical town with the castle, an old castle to the left. But the importance is that it's in the middle of the urban fabric. To the right of the treatment plant is actually immediately next to it is a food processing plant. This kind of juxtaposition is only possible because the treatment plant is small, doesn't smell, and it's actually aesthetically appealing. You can see inside the treatment plant, the old castle shows through the glass, or the control room. But of course, in addition to municipal treatment plants, you can use this solution for commercial developments, as you can see on this one, or for campuses, or for residential developments. This park setting on the left-hand side, you can see the treatment plant, the Organica plant. Or this example is for the contract manufacturer Foxconn. It's in China. The treatment plant sits and connects to the urban fabric seamlessly. In the interior picture, you can see through the glass and you can see the proximity of the residential buildings. Again, from the residential buildings, from the apartments, they look at the botanical garden. This example is that of a poultry processing plant, which shows you that the Organica solution is not only applicable to sanitary sewage, but also to certain kind of industrial flaws, where the wastewater stream is of organic origin. And there is an interesting phenomena that we see everywhere we build these treatment plants, that there is a tremendous interest on the part of the public to come and see and learn, whether these are kindergarten visitors or university students or people from the professional community. The Organica treatment plants can be thought of as a place of visit and the place of learning as well. Special kind of application is when we take an old treatment plant and we'll retrofit, we fix it up, we increase the capacity. And the example I'm going to show you is a treatment plant that was built 50 years ago, serves 500,000 people. It's about 80,000 cubic meters in capacity. What you can see on the picture is a typical activated sludge plant with 3 trains. You can see the primary clarifiers, the aeration, the biological reactors, 2 secondary clarifiers on each. Over time, they built a nitrogen removal system, a biophore. And on the left-hand side of the slide, you can see the anaerobic digestors. Now, over time, the anaerobic digestors not only started to serve as a way to digest the sludge, but the operators started to bring in additional high-strength waste. And today, they produce, in the anaerobic digestors, twice the amount of biogas than what they need to run the treatment plant. In effect, the treatment plant became a little bit like a small power plant. The side effect of which is that there is a very high strength leachate coming out of the digestors. So you can take a look at the process scheme, a very simplified process scheme here. We have the wastewater treatment plant and we have a waste to energy plant. That high strength waste that is coming out from the digestors actually increased the load on the treatment plant, sometimes 40, 60, or even 100%, depending on what component we looked at. And our task was to increase the capacity of the treatment plant without building new reactors. So let's take a look at, this was the original layout. Each of the 3 trains looked like this, which actually 2 sides to each. And this is the cross-section, a typical activated sludge plant. And what we did, we filled the reactors with partially with natural media, which is the plants, and also with biomodules, the artificial media, adjusted the aeration, and of course, enclosed the entire plant with the greenhouse. With this kind of intensification, we were able to increase the nutrient removal capacity by 50 to 100%. On the layout, you can see on the lower part of the slide, there is a little bit of educational annex, which is a feature that we are increasingly asked by our clients to provide, because these treatment plants, these facilities, attract a lot of visitors. You can see during construction here in the distance, you see the anaerobic digestors. You can see the plant tracks and the biomodules. This particular picture shows you during construction when the reactors are emptied, and you can see the biomodules. And this is what the architectural rendering looked like. And voila, here's the built treatment plant with a few exterior shots. In the interior shots, you can make out standard features of the greenhouse. As I mentioned earlier, the greenhouse is come prefabricated with all these components. It's off the shelf. You can see the shading structure or the shading curtains on the roof. These serves as energy shields in the winter months and as sun shading during the summer. And you can make out the misting equipment, which helps to maintain the outside temperature during the hot summer months. In this particular case, you can also see solar panels on top. So the client was eager to enhance the sustainable aspects of the renovation, and the part of the roof of the greenhouse is covered with solar panels, helping to even further reduce the energy consumption. And of course, where this treatment plant was built, the winter gets very, very cold. But that's why we have the greenhouse. So even when the temperature outside drops below 20 or 25 degrees centigrade, inside it's easy to maintain the 6 to 8 degrees, because there is a tremendous thermal inertia of the wastewater itself. So very little additional supplemental heat is needed to maintain the desired temperature. And of course, you can imagine that once you refurbish or retrofit an old treatment plant that used to be smelly and used to be ugly, now, with this kind of appearance, you can start to develop the neighboring real estate, and actually the value of that land will increase. With this kind of solution, it's very easy to integrate the treatment facility into the urban fabric. What we will see in the next few slides is examples for that. And of course, urban integration means that you don't have to pump the water away from the cities. It can be reused inside the city, and thereby saving tremendous infrastructure cost as well as operational cost. This example is in China. You can see the residential towers in the back, and right next to it, there it is, the treatment plant. From the other side of the street, you can see that there are office buildings with the necessary restaurants downstairs and the treatment plant on the right-hand side. In the back side, there's a basketball court. Fits very nicely with the treatment plant next door. These are the interior pictures. Or this is a development in the middle of a large city. It's actually in Shenzhen, China, where in a city block, as you can see, there are residential towers, office towers, and in the middle of the development, there is a multi-level, semi-open mall with all the fancy stores left and right. And if you close up, you see that in the middle, there is a tiny little greenhouse, because the developer was very eager to do this in a sustainable way. And all the water that's used in this development is being treated right on the site in the middle of the mall, so that the water can be reused inside that city block. And you can see it's like a little jewel. It enhances the development. The next example is on a tropical island on Hainan Island in southern China. And you can see this is a resort, and the treatment plant is in the middle of the traffic circle. Here you can see the plant, the Organica plant during construction. On the right-hand side, you can make out this little building, which is the stairs going down to the mechanical room. And here is the treatment plant with the plants on top in the traffic circle, with the residential towers looking directly down to the traffic circle, which is treating all the water so it can be reused for irrigation. Or this example is in a fancy villa park in India. You have to imagine fancy villas to the left and houses to the right, and this in the corner treats the water for about 1,000 cubic meters. But again, this allows a very different level of urban integration. Or the next example is a larger capacity, 45,000 cubic meters a day capacity plant. This is for one of the largest industrial and logistical parks in Indonesia. The entire plant is occupying about 10,000 square meters. which for the capacity is a very small footprint. And immediately next door, high-value real estate is being sold to the largest Japanese companies. In the pictures, you can see the entrance area to the treatment plant. And this is a very good example to show you that in climates where the greenhouse is not necessary, where the temperature doesn't drop below 10 degrees centigrade, the plants are protected by shading structures. So the next example is in China, in Shandong province, directly on the beach. What you see on the right-hand side is a visitor center, and you can see the treatment plant blends into the environment very nicely. With the Organica solution, a whole new level of urban integration is possible. In other words, the urban water cycle can be made truly sustainable. And what you see in the next few slides is examples for solutions that can be in really highly dense urban areas. Once you make your way to Main Street, a different level of architectural demand will arise. And the kind of aesthetic appeal that you find natural when you look at a museum or a school or an office building, the same kind of demand will be applied to these water reclamation facilities. We did a little study, a simple study, to see that what can a water reclamation facility look like if it's put smack in the middle in one of the densest urban areas on Earth. And so we picked Manhattan, one of the densest urban areas on the globe, the corner of 8th Avenue and 26th Street. This is a small parking lot today, and we took a design that would serve 100,000 people. And what you can see here is that in this solution, there are two trains, as you would do that in any traditional approach, except that these trains are in a staggered way, and in between the two trains you see the mechanical area. And the mechanical areas are done in a way very much like a loading berth for a large supermarket that serves a lot of food with a meat section and vegetable section. And the loading berth of those supermarkets are not very nice, and they tend to be smelly as well. Now the same principle, design principle, applies here. The trucks go through a large door, and all the odor is treated internally. And all the mechanical equipment is hidden from sight, efficiently stuck between the two trains. You can see how the trains are staggered, how they get the plant racks on top. And of course, if you are in the middle of the city, you might as well have an observation desk, because it surely will attract a lot of visitors, with an elevator tower. And then you see the plants, and you can make out a little ramp that goes up in these hanging gardens. And of course, you need to enclose to maintain the desired temperature. And voila, here you are. This is your water reclamation facility in the middle of the city. And as you can see, this serves not only to reclaim the water, but also as a space that gives room for plants, for recreation, for education, and helps to convert the concrete jungle into something green and much more sustainable.